Wonderful. So, my guest today has spent over 20 years arguing that everything we think we know about cancer is wrong. Professor Thomas Seyfried. Welcome to Rewind Yourself, and thank you very much for joining me today.
Oh, thank you, Matt. It's nice to be here today. Thank you.
Wonderful. Maybe we can start with the first question, and you can tell us a little bit more. What drew you into cancer research, and was there a particular moment or experience early on that set you in that direction, starting in the field you're working and work for the past 2 decades, over 2 decades?
Yeah, probably more like 4 decades.
Okay.
Well, we did our first studies on cancer in my first paper published in 1987. We were working on ganglioside biochemistry. I actually got a book here from most of the folks in this book are dead. Someone just dropped it off to me, an old book on ganglioside bio. Oh, I don't know if you can see it the right way. Oh, a structure and function of gangliosides. Do you know what gangliosides are?
No, no.
Well, that was interesting because I got my PhD from the University of Illinois on ganglioside biochemistry in neurological mouse models. So there's some diseases in humans called Tay-Sachs disease, which is an old disease recognized back in the 1800s. It's a neurodegeneration disease. Neurons die because they accumulate these glycolipid molecules called gangliosides. And the children will die at early ages. I was always fascinated by the complexity of the structures of these molecules. And I was interested in brain degeneration and neurobiology and epilepsy and all this kind of stuff. And when I went to Yale University after I got my degree, I worked in a leading edge research ganglioside biochemistry, and I was doing glycolipid isolation and purification and analysis of these molecules. But the department I worked in was an epilepsy department. So if you wanted to stay at Yale University in that department, you needed to do something with epilepsy. So we started looking at gangliosides in the brains of epileptic mice, and mapped genes for epilepsy. We did all this kind of stuff. And then at the same time, we were trying to figure out what these molecules do. What do these gangliosides do? They're in the brain. They're heavily in the brain. So we got some brain tumor tissue from people and mice, and we started to look at the gangliosides in the brain tumors. And of course, it was hopelessly complicated. It was really, really very, very complicated. And we had the best lab in the world to isolate and purify and analyze these lipids, and it was just so complicated. But we learned a lot from that, but it wasn't anything to manage cancer. We weren't, at first, it was purely what we call basic research. It was not designed to say, oh, studying gangliosides may help people live longer who have brain cancer. However, during the craze, there was a big focus in cancer in the year 2000, around late 90s, early 2000, on angiogenesis. Angiogenesis is abnormal vasculature in cancer blood vessels. So we found that there were abnormal gangliosides linked to the abnormal blood vessels. So that brought us at least a little closer to saying, oh, one of these ganglioside molecules could play a role in angiogenesis, the abnormal vasculature in tumors. And then we had a mouse model that had highly spontaneous brain tumor that was very similar to glioblastoma. And we changed the ganglioside pattern, and it stopped metastasizing and invading. So there was another link between gangliosides and cancer, and it was mostly brain cancer stuff that we were doing. But we, as I said, we were paralleling our work with epilepsy and ganglioside biochemistry, and then we realized with the angiogenesis that if you calorie restricted people, uh, water only fasting and this kind of thing, the angiogenesis would become much less. And we found that not only did the angiogenesis become less, the tumor shrunk. The tumors would shrink. So very interesting. It's really kind of an embarrassing story. I was working with a drug company that had a drug that blocked ganglioside biosynthesis, and they thought they would have a blockbuster drug to manage cancer, and they gave us substantial amount of money to investigate this drug and the ability to target gangliosides and shrink angiogenesis. Um, but what happened was we gave the drug to the mice, and the tumors got smaller, and the gangliosides were reduced along with the size of changed the ganglioside pattern. They were all excited. They said, "Oh my God, we have a drug that blocks ganglioside biosynthesis and makes the tumors get smaller. We could make billions of dollars on this drug." And what we noticed was something very strange. When we fed the drug to the animals, um, they ate the drug. They ate the. We had to mix the drug in with the food, and we put the drug in with the powdered food, and the animals would eat the powdered food and the drug together, and the tumors would shrink. But the body weight of the mouse was shrinking as well. The mice simply got smaller while they were eating the food with the drug in it. And the gangliosides in the tumor were going down. So we said, wow, this is really interesting. What's happening? And then I said, well, we have to put a body weight control in. We have to put another group of mice that would be restricted in the amount of food they ate, so their body weight would be comparable to that of the guys eating the drug. So we had one group of mice eating the drug mixed in the diet, and the tumors shrunk, and the mice got body weight got smaller. So the other group of mice, we just restricted the amount of food to match their body weight, the body weight of the two groups. The tumor shrunk to the same degree, but it had no change. The gangliosides were not changed at all from that. So it turns out that the drug entered the stomach of the mouse and prevented the mouse from digesting the food. So they were eating food, but they were not digesting it. So therefore, there was kind of an indirect starvation. Um, but we found out that it had absolutely nothing to do with the drug. It had everything to do with how much food the mice were eating. In one group they couldn't digest the food, and then the other group they weren't given the food to digest, and the tumors shrunk to the same extent. In one group the gangliosides went down, and the other group the gangliosides didn't go down. So the whole effect had nothing to do with gangliosides. It had to do with the amount of food the animals were eating. And then that brought us to Otto Warburg. He said a long time ago, if you cut calories down, blood sugar goes down. The tumor needs sugar, and the tumor. So when I told the drug company that this was all an indirect effect of calorie restriction, they immediately dropped it. They said, "Oh, no more money for you. We don't want any part of this. It's not exciting anymore. It's a purely calorie restriction thing, not an effect of our beautiful, which our multi-billion-dollar drug that they thought was going to make all kinds of money." But it was all a calorie restriction. And then we went back to Otto Warburg, and he was saying this a long time ago. He says cancer cells are driven by sugar. If you stop eating, blood sugar goes down. Blood sugar goes down. You get it's an anti-inflammatory effect. It has all kinds of beautiful effects. And we were seeing everything from calorie restriction, which then led us to ketogenic diets. So we were brought into this whole field by indirect observations from different disciplines. So that's how we got started with this.
Okay, wonderful. And was this the moment you felt like the genetic theory of cancer wasn't the full picture?
Well, that was what everybody was brainwashed into thinking cancer was a genetic disease. I did too. I mean, I never questioned when I taught genetics. I have a PhD in genetics, and when people said, "Oh, they were all excited about gene mutations in cancer and following the mutations and everything," I never thought there was a problem with that. I mean, I taught the same, mindlessly. You read textbooks, and the textbook said it's a genetic disease, and you mindlessly communicate that information to other people because it's in the textbooks. But then, when I started to see how powerful calorie restriction was to shrinking the tumor, and it didn't make any difference, what kind of mutations were in the tumor. When you stopped eating food, the tumors would shrink, the angiogenesis would go down. It didn't seem to have any relevance to the tumor, to the genomic or the mutations in the tumor. And then when we started to look at this in more detail, I noticed some inconsistencies with the field, which said that cancer was a genetic disease. But then when I was looking at these experiments where you transplant the nucleus from one cell to another cell, so when you take the nucleus from a tumor cell and put it into a normal cell, you didn't get dysregulated growth. But if I took the nucleus from a normal cell and put it into the cytoplasm of a tumor cell, you got dysregulated growth, suggesting that, and many other studies that were like this in frogs and mice and in vitro and in vivo, it seemed to argue directly against the gene theory. So, and I'm seeing powerful therapeutic benefits from calorie restriction and restricted ketogenic diets. And I said well, this whole doesn't make any sense anymore. The whole genetic study of cancer makes no sense when you start looking at the data. And one thing led to another, and I said, why are we chasing genes? They have nothing to do with cancer. And then when I started to look at the mitochondria of cancer, they were all defective. The mitochondria and the cells were. Why the cancer cell was growing so fast is because it was making energy based on a fermentation, energy without oxygen, which was due to mitochondrial defects. So I said that all cancers have the same problem. Why are we chasing genes when they're all a mitochondrial problem? And then once you realize that, the cancer cell must have the sugar glucose, and what we discovered was the fermentation of the amino acid glutamine. And then I said, what difference does it make what kind of gene mutations they have? If you take away glucose and glutamine, the damn cells die. And they can't burn ketones or fatty acids. So all other things are irrelevant. And this is the biggest problem that the cancer field cannot accept. They are still mindlessly chasing genes. When the horse is dead and you beat the horse with a stick, a dead horse is not going to get up and walk. Unfortunately, the cancer field doesn't understand that. So they continue to spend billions and billions of dollars on things that are largely irrelevant to the nature of the problem. The issue is that the drug companies, the academic industries, the hospital industries have all wrapped themselves around this worldview that cancer is a genetic disease, and if we target these mutations, we're going to have success. And the answer is yes, you do have success in a very few number of people, but the majority of people don't respond. But they will respond to a simultaneous restriction of the sugar glucose and the amino acid glutamine. We've shown that over and over again. Not only mice, humans. So we know what I have a fairly good understanding of how cancer starts, how it progresses, and how to manage it with minimal to no toxicity. The problem is the rest of the field either doesn't want to know that, or can't understand that, or refuse to understand that, because it's too devastating to an entire industry to have that kind of information.
Okay. And so when did you begin to develop the metabolic theory? Do you have any sense of how much resistance it would face as well?
Well, we started it from the epilepsy because the same problem. I was mapping genes for epileptic seizures in mice, and we were hoping to take that knowledge and see if we could find the same kinds of mutations in humans with epilepsy and use the same kind of strategy, target the mutation or fix the mutation, to see if you could stop the epileptic seizures. So we were using ketogenic diets, and it was interesting. It didn't make any difference what kind of seizures the kids had or the mice. The diet would reduce the amount of epileptic seizures. So again, another situation where it didn't make much difference. Even though the mutation may be contributing to the epileptic seizures, you could still manage the seizures despite the continued presence of the mutation using a ketogenic diet. And that goes back to 1921 with Wilder at the Mayo Clinic. It was a fasting mimicking diet. It was a ketogenic diet, and it blocked epileptic seizures. But it also blocked the growth of the tumor because the tumors needed the sugar glucose. And that was another thing. We knew in kids with epilepsy, having a low, steady glucose was essential for managing seizures with diet. You have to have a low, steady glucose. If the kids took some sugar in, like a juice or a candy bar or a cupcake, sugar went up high, and immediately the child would, within a few minutes after eating, the child would have an explosive seizure. So you saw immediate the impact. With cancer, and you have a tumor that's managed and you eat sugar, you don't see the tumor growing immediately. It takes weeks or months for it to grow. But it was still the same thing. We've never figured out completely the mechanism by which ketogenic metabolic therapy manages epileptic seizure, but we have a crystal clear picture of how this blocks tumor growth. So it becomes much more clear on how metabolic therapy shrinks tumors than how metabolic therapy stops epileptic seizures.
Okay, wonderful. And what evidence keep coming back to as the strongest support for your view? Is there one?
What, the strongest support that cancer is a mitochondrial metabolic disease?
Yes.
Okay, so all cancer cells that we've looked at, whether in human tumors or mouse, they have abnormalities in the number, structure, and function of mitochondria. All major cancers grow on a fermentation. They use glucose and glutamine fermentation, which means energy without oxygen. So these are all of the major features. And of course, if you target and restrict the two fermentable fuels, glucose and glutamine, you get shrinkage of all major cancers. So all of these together show that this is predominantly a mitochondrial metabolic disease. Every cancer that you look at has a totally different genetic mutation profile. So no two cells in a tumor have the same genetic mutations, but every cell in the tumor needs to ferment glucose and glutamine. So this is the linkage.
Okay, understood. And so why do you think the metabolic theory has struggled to gain wide acceptance in mainstream oncology? Do you think it's all related to crashing the industry and the money they gain, or?
Well, I don't know about that. I think the issue is the several. You're talking about a paradigm change here. You're talking about institutions that have built major departments on cancer as a genetic disease. You have very lucrative procedures for managing cancer in the clinic. Many of these things are very, very expensive. There's a lot of people. You have an enormous juggernaut of drug companies building drugs, all based on the gene theory. So you come along and you say, maybe it's not a genetic disease. And this is not what the institutions, what the system wants to hear. They don't want to hear it because it's too disruptive. So what we know is that when you take people with cancer and put them into a new metabolic state, you can still use chemo and radiation and this kind of thing, but you use it at a much different way. Much lower doses of drugs, much greater intervals between treatments, and you get a better effect. So what's wrong with that? And what's more important, you empower the patient to manage their own disease. So they work with the oncologist, the patient and the oncologist work together. But the big problem is the oncologists have never been trained to know that cancer is a metabolic disease. So they're treating patients based on what the field told them what cancer was and why they have to do what they do. So we have a problem with lack of knowledge on the part of the practitioners, lack of knowledge on the part of the patients. So it's a very unsettling situation. And in the United States, we have over 626,000 people are projected to die this year from cancer, which comes to about 1,700 people a day dying from cancer. Most of this doesn't have to happen, but it does. Many people are treated so harshly with chemicals and radiation that their bodies can no longer recover from the poisonous and toxic treatments. Many cancer patients that do survive the toxic treatments, many, not all, can have recurrence of a tumor later in their life somewhere else. Many people who are treated this way suffer from the toxic treatment. So they have diseases and afflictions from the treatment rather than from the cancer. Up and down, you can go and say this whole cancer thing is one of the greatest tragedies in the history of medicine, because they have been treating cancer patients with therapies based on an incorrect theory. And when the theory is not correct, the outcomes will never be optimal.
So, do you think the way scientific research is funded makes it harder for unconventional ideas to be taken seriously?
Well, I mean, I don't know. You have to ask oncologists and get a feel for what they think. When I debate oncologists, they seem to be locked into this gene centric way of view, and then when you bring up issues that are incompatible with that, they seem not to know, and they get embarrassed because they were never told this. And the other thing too is oncologists are working every day with cancer patients in the clinic, and they don't have really time to read the scientific literature. Unless someone has a conference and tells them that this is not the best way to treat your patients. People get upset. They've been trained, they spend a lot of money, they think they know what they're doing, and then someone comes along and says, there's a very, very different way to do this to achieve greater success in your patients. And where's the clinical trials? How come you don't have any clinical trials? Well, if we had the money, we would definitely run a clinical trial, because we're the best in the world to do that. But then they say, well, we're going to give money to one of these big hospitals, let them run a clinical trial, and the results don't look good because they have no clue what they're doing or how to do it. You really need skilled. You have to really know. We developed all the procedures for managing cancer as a metabolic disease, and we've done enough clinical studies, case reports, to know what to do and how to do it. But the big governments haven't come forward and said, okay, your group, which is my group, because we have the best trained people here and the most knowledgeable people, you guys run the clinical trial. We run a clinical trial, you're going to see remarkable effects. We know how to get people into nutritional ketosis. We know how to use chemotherapies at lower dosages. We know how to do this stuff because we have case reports, we have preclinical evidence and human case reports to run a clinical trial to be very successful. It's really weird. When you look at the clinical trials that have been done with keto metabolic therapy, their biggest issue is whether it's harmful, whether a calorie restricted keto is harmful. And yet they're treating these poor people with high dose radiation and toxic poisons. That's harmful. I mean, the diet is the least harmful part, and they're more worried about the diet causing like cardiovascular. These people got 1 month to live, and you're worried about cardiovascular disease from a calorie. I mean, this is the crazy stuff you hear from these people. It's not their fault. It's just what we call a profound lack of knowledge on the biology and biochemistry of the disease they're working on. And we have a tragedy. The tragedy is all these poor people dying and being brutalized by therapies that could be easily modified to get maximum benefit, but they're not doing that.
Okay. So what would it take for science to change its mind?
More and more evidence. You just keep pounding the data. You just doing the experiments over and over again. Okay, let's try pancreatic cancer. Let's try breast cancer. Let's try bladder cancer. Let's try melanoma. Let's try glioblastoma. Let's try lung cancer, triple negative breast cancers. You name it. Let's try multiple myeloma. What about all the blood cancers? Let's try that. And every time you do it, you get a better result when you do metabolic therapy together with drugs. Eventually, it'll change because you know why? People want to live. Guess who wants this? The cancer patients want it, and they go to their oncologist and they get slapped down. Well, I never heard of this. This. So the people are learning more about this, and the other thing too is the people become empowered. They know when. Now, not everybody. Our big trial, a big study we did not long ago, 2025, published in Greece with glioblastoma, one of the most deadly brain cancers you can have. Very rare, very, very low survival after 5 years, very low. We put some of the patients on a Mediterranean ketogenic restricted diet, and the diet was salmon, avocados, sardines, olive oil, and nuts, like pecans and walnuts and this kind of thing, almonds, and 4 out of the 6 people in that group survived 3 years or longer. 12 people took standard of care. Well, let me say we have temozolomide, which is a toxic poisonous drug, and radiation, and no keto diet. The other group had radiation and poisonous chemical plus ketogenic metabolic therapy. So the guys in the ketogenic metabolic therapy, 4 out of 6 of the people lived 3 years or longer, and the guys in the standard of care, which was radiation and toxic poison, only 1 out of 12 survived 3 years. Striking. If that were a drug, they'd be breaking the doors down to give this drug. It's not a drug; it's a metabolic therapy. So there's less. And listen to this. Several of the people in the standard of care group refused to give up sugar. They would rather die than give up the sugar in their coffee and stuff. And they did die. I mean, it's the choice of the person. Believe me, some of these people they did not want to go and eat salmon and olive oil and sardines. They prefer to have high carbohydrate breads and all this kind of stuff and sugar. And only 1 out of 12 guys, by the grace of God, survived 3 years. And the guys who gave it all up and did metabolic therapy had 4 out of 6 lived 3 years or longer. Some are still alive. So clearly, is striking difference, and it works for lung cancer, colon cancer, breast cancer. You get tremendous results when people make these shifts, but they're not encouraged to do that. At least they are in certain small clinics and small groups. But we want it to eventually become the standard of care. It should be the standard of care at some point.
Okay. And so what area of cancer or metabolic research excites you most right now? Is there an area?
It's the future. It's exciting because it will be the future. It's the coming. Ketogenic metabolic therapy for cancer. We developed now a tool called the Glucose Ketone Index, the GKI. We developed it here at Boston College. It's a ratio of the glucose in the blood, the sugar in the blood, to the amount of ketone body, which is it's a fat breakdown product called ketone body. The ratio of the sugar to the ketone body can predict your overall degree of health. It can allow you to prevent cancer and many other chronic diseases, or allow you to manage it, depending on what zone you're in. The lower the GKI, the more healthy your mitochondria become. The higher the GKI, the less healthy your mitochondria become. Mitochondria health, the mitochondria in the cell, which is the organelle that controls the destiny and the energy and the efficiency of the cell. If that organelle can remain healthy, you live longer with a higher quality of life. Cancer cells will die. Your overall survival is increased, or you can prevent cancer and chronic diseases from happening in the first place. As a young person, you start monitoring your GKI, and you keep it in these low zones, and you prevent cancer, you prevent dementia, you prevent cardiovascular disease, you prevent obesity, you prevent type 2 diabetes, and consequently you live longer. But it's all depending on the person, whether they want to do that. Do people want to live longer or not? You're in control of your own destiny, but you have a quantitative tool to allow you to make decisions for yourself. Just like the guys who wanted to drink sugar, they would have a high GKI and they would be dead. And that's what happens. And if they wanted to live longer, they would have a lower GKI, killing tumor cells, enhancing the health of the mitochondria. And that's their choice. It's the choice of the individual as to what they want to do. And believe me, it's not easy to get into the dark green zones that will kill cancer and manage a lot of chronic diseases. Or you can prevent these by living in a yellow zone, which is a little bit higher than the dark green zone, keeping your mitochondria healthy so you never have to have these diseases in the first place. This is going to come out this year. It's under review right now. And it will be a worldwide tool for everyone to measure their own ratio of sugar to ketone in the blood, which will give them a clear path or a chart as to how healthy they will be, and if they want to manage cancer, how effective they can manage it.
Okay. So if your work is ultimately proven correct, how do you think it changes the future of treatment?
Well, people will live longer with a higher quality of life. They'll exist on the planet for a longer period of time. I think there might be some value to that.
But you still get
I
those
don't
stubborn
know.
people.
I don't need to make any money. You see, I need money only to conduct the research that I do, so that we can improve, and streamline. We want this to be as seamless as possible, and show how diet drug combos are great for the various kinds of diseases. Um, we need money. We need money to do that. We have philanthropy, private foundations, and philanthropy are very excited about what we do, and they want to be part of the paradigm shift. And it will happen. It will happen because it's based on the correct science, the correct theory, and the desire of people to want it. So we have everything. The only thing we don't have is the system willing to make the adjustments necessary. So that's the only stumbling block right now, is the ability of the system to adapt.
Okay, so do you think this is the biggest misunderstanding the public has about cancer today? Is that the
Oh, absolutely. If you ask people about cancer, regardless of what country you're in, they're going to tell you it's a genetic disease, and I'm telling you it's not. And they're going to say, "Well, how come you know?" Because I did the research, I have the science, and it's not just me. It goes all the way back to the work of Otto Warburg in Germany, one of Germany's greatest scientists. You have to realize the history of this guy. Uh, Warburg was the first major figure in the cancer war around the world. It was in the 1920s. And the Second World War, Warburg was a half Jewish. His family was of Jewish origin. And, um, and during the Second World War, Hitler spared Warburg. Hitler feared cancer. Hitler didn't want, his mother died of cancer. He feared cancer. He knew Warburg was the only guy on the planet that was going to cure cancer. And he said, "What are we going to do? Gas this guy? Are you kidding me? We're not going to do that." So they kept him alive, and uh, and he was right, but he wasn't right completely. We went back and we looked at Warburg's work, and we found he said it was a mitochondrial metabolic disease, not a genetic disease. He said that. But he was discounted after the Second World War. They all ran off the field. The world cancer people ran off chasing genes, and thought Warburg was made some errors. He did make errors, and there was confusion. We went back and we cleared up the misunderstanding and the confusion. We now know that Warburg was basically right, but he didn't have all of the facts put together correctly. Um, so now that we have done that, we can now go back and manage cancer the way it should have been managed at the very beginning. So we lost 100 years of dead people and suffering as the result of this. And I don't know how much longer it's going to take for the field to adjust and adapt to the new reality that this is a metabolic problem. And we're not going to throw out immunotherapies or radiation or chemo. We're just going to use them in a different way, in a more effective way, less toxic way. So we're going to use all the tools we have. We just have to let people know what's going on and let them look at the data.
so would you have done things differently in how you pursued, published, or communicated your work then?
No, I don't think so, because how we came to this was no one could plan this. No one could say, this is the plan, this is the strategy. You just have to look at what others have done, and then you have to use your rational capability of knowing what makes sense and what doesn't make sense, and then design experiments to test it. So there was no way I could have predicted this. Um, I probably, if I didn't work in the field of epilepsy or gangliosides, we may never have come across these linkages. So who could predict anything like this? It's you follow observations, and then you start to make connections between observations, and things start to make more sense, and then you design to test your hypothesis. You design experiments to see whether or not your ideas are supported by the scientific evidence. And when it is, and you don't necessarily have to do all of the work, uh, uh, like the nuclear mitochondrial transfer experiments, for example, those experiments were not done to test the somatic mutation theory. They were done just simply to ask if a cancer nucleus can direct normal development, and it can up to a point. They were, but they didn't recognize that the outcome from those experiments undermined an entire worldview of what the nature of the disease was, and they were still groping on how to explain the nuclear mitochondrial transfer experiments based on the somatic mutation theory, and they couldn't. So what they said, oh, it must be epigenetic. Whoa, okay, that's a nice term, epigenetics. When you're really caught and you really can't explain something, it must be epigenetic, and everybody then feels like, oh, okay, that's what it is. But that can be anything and everything and its opposite. So you really need to know what that means itself. Design an experiment, and it turns out that the mitochondria are the most powerful epigenetic system in the cell. But there's intranuclear epigenetics and extranuclear epigenetics. And then when you start looking at it in that direction, you can start putting everything together once you understand the biology and biochemistry of the problem. And that's what we do. We know the biology and biochemistry. We can track down almost every kind of cancer, where it came from, how it started, how it progressed, how it goes through these different phases, and most of all, how to kill it without toxicity. That's what we can do. We never use the word cure. We don't cure cancer. We manage cancer. Okay. So we have people like Pablo Kelly from Devon, England. He had a glioblastoma and he lived over 10 years, never cured. His tumor was always there, but he lived 10 years. He had a family, and he died from a brain bleed trying to surgically debulk, fourth surgical debulking. So he never died from cancer, but he was never cured of cancer either. But he lived far longer. So we're in the business of keeping people alive longer. If it goes away and you die of old age at 98 years old from a heart attack, and your cancer never came back, okay, then you were probably cured. But we don't know that. All we know is that the disease is not apparent. And if it is apparent, it's indolent or it's growing very, very slow. So either way, we never say cure, we say effective management. Can we effectively manage cancer? Absolutely. Can we cure cancer? We don't know. So that's what people say. Oh, now Seyfried says he can cure cancer. I've never said that. I said what we can do is manage cancer. And they say, oh, ketogenic diets can't cure cancer. Well, of course they can't. Any fool would know that. But can they manage cancer? Yes, they can manage cancer. So people have to know the difference between curing and managing, and they have to be smart about it. Can't be stupid about it.
All right. Thank you for clarifying this. And so looking at your career, what's the proudest moment throughout your career? I mean, was it the beginning of the research you conducted and everything, or was there anything else you would say in particular? One?
Every day we see something new, and we try to follow it up and ferret it out. So it's a constantly emerging realization, and we're getting new and exciting data as we speak. So it's always exciting to see. There are setbacks, of course, like anything. Somebody tells us they have this wonderful drug and we need to try it, and they give me $65,000, and I try it, and then I have to tell them it doesn't work, and they get all upset. It's a setback for them. It's not a setback for us. They just have these ideas that something is going to work, and they do that, and we test it. It doesn't work. But when we test things when we know how things work and we can see things targeting glucose and glutamine, we know that you're going to have some level of therapeutic benefit for that. So it's exciting. Every day is a new day in the lab. Something new comes up every day.
Okay, wonderful. And so if a 25 years old is watching this and feels like the system, whether in medicine, science, or their own career, isn't listening to them, what would you say to them? Because you've probably faced a lot
I
of
would say,
problems.
well, one of the problems is that people don't read the papers. It's human nature to have someone tell them about it rather than them investing the energy and time to do it. So a lot of problems come by hearsay and speculation about things. we publish all of our papers open access. That means anyone who would have a computer could get our papers and read them. Um, but when you read some of the heavy science that we write, some people, their eyes glass over and they say, "Oh, I can't really understand what he's talking about. Maybe I'll ask this guy sitting over here what he thinks." And the guy has an opinion that's completely erroneous, and then he spreads information because of his lack of knowledge. So, and this happens in the scientific field. For example, I published a paper on the origin of metastatic cancer metastasis. This is the process by which cancer cells spread around the body. And and I said in the paper that most people die with cancer because it spreads around the body. So my paper, which explains the mechanism of metastasis, how some cancer cells fuse with an immune cell, and that hybrid cell becomes the metastatic cancer. Um, uh, when you it was my paper was cited over 1,700 times by people who just cite it because I said metastasis is the most deadly part. They don't cite it for any of the science inside the paper. They never read the science, so it tells me that a lot of scientists are not reading the papers themselves. They're just citing it for one phrase: metastasis kills most people, and they keep citing my paper over and over again. But they never read inside what the paper actually did, and then they go and publish something completely different. So that tells me that the scientists themselves are not reading the science. They're not reading the science. If it doesn't agree with what they think, they're citing it for something that's completely irrelevant to the nature of the problem. We know what metastatic cancer cells are. We know how metastasis happens, and we know how to kill metastatic cancer cells. But but for whatever reason, they're not the people in the field aren't reading this or understanding it or wanting to understand it. So it's a complicated human uh, failure. It's an ability of humans to not use rational thinking when they do this, when they look at these things.
Okay. And since we're living in the time of artificial intelligence, how do you feel about the future? Is it going to help you, replace you, eliminate, support?
Oh,
What's your
artificial
take on it?
intelligence. AI is a tool that's very valuable for us, but you can easily see that many humans can be controlled by AI. AI does not have rational thinking, and that's one of the characteristics that we have that the other animals don't have. Um, Chimpanzees and gorillas and these kinds of things, they're smart animals, but what they do is basically hardwired. They don't have rational thinking the way we do, and indoctrination, whether it's political, religious, or scientific, removes rational thinking. So AI does not have rational thinking. AI can do an awful lot of things, but they can't think rationally. And unfortunately, most humans on the planet don't also think rationally when they become indoctrinated. Solidification of the brain, preventing a reevaluation of things that may go against their indoctrination or their brainwashing. And that holds humankind back for a variety of reasons. But the scientific community also suffers from the same problem.
Okay. Thank you for clarifying this. So, apart from everything I've asked in the interview, is there anything you would want to leave our audience with? Whether this would be, words of wisdom, so anything maybe I haven't covered and you think it should be out there and people should, listen and
Well,
take it.
I think there's hope. I think for the cancer field and for chronic disease management, there's tremendous hope. Um, we can eliminate or significantly reduce many of these chronic diseases which are afflicting the world populations today. Give them tools. We're not going to force people to do things they don't want to do, but we can give them the tools to allow them to do what they would like to do in a positive way. There's a very big difference by forcing people to do things they don't want to do, rather than okay, here's the tool, you know how to use it. It's your choice as to whether you want to do it or not. And I think that will be the great transformation that we have coming for managing chronic diseases in cancer. I mean, I can't speak to uh, political activities of countries and things like this. That's out of my sphere. But at least when it comes to managing chronic diseases, we can certainly speak to that, and the future looks very hopeful.
Wonderful. Professor Seyfried, thank you very much. I really appreciate your time answering all the questions, clarifying things. And I hope it will leave the audiences more educated, knowledgeable, and hopefully they will apply what you shared with us today. So thank you very much for this. I truly appreciate it.
Well, thank you. Thank you very much. A real pleasure.